Chapter 1: Critical Thinking. In this section we'll discuss public policy and Simpson's paradox. Is average always average? We'll start with an example. The following table shows the number of workers in thousands in the first quarter of a given year. These figures are for the workers 25 years and older in the United States in two educational subgroups: those without a bachelor's degree and those with a bachelor's degree. Here we have two tables for the year 2000 and 2013. From the total figures, it appears that the total weekly earnings, have increased in 13 years. To tell whether the figures have actually increased for the workers, we have to compute total weekly earnings per worker in each category, right? So we'll take a category here, earnings by people with less than a bachelor's degree divided by the number of people with less than bachelor's degrees. We'll do that for all the categories. Show that from 2000 to 2013, the average weekly earnings per worker decreased in each educational subgroup, but increased overall. Round each average to the nearest dollar. As I mentioned in the previous slide, we first find the average weekly earnings per worker in 2000 for those with less than bachelor's degree first. We have average weekly earnings equal to total weekly earnings divided by number of workers. Let me go back by the slide. We have this number divided by this number. The average is about $646 per worker. When you do this for all the categories, we can summarize the average earnings per worker for all categories. As you can see, for people with less than bachelor's degree, earnings have decreased from $646 per week per worker to $593 per week per worker. And for people with bachelor's degree or higher, the earnings per week per worker have decreased as well, from 1,203 to 1,189. Now if you look at these figures overall, if you take the weekly earnings by the entire population divided by the total number of individuals in the population, we have an increase in average weekly earnings. For both educational subgroups, the average weekly earnings decreased from 2000 to 2013, but overall, the average weekly earnings increased. The previous example was the example of the Simpson's paradox. Simpson's paradox occurs when combining or aggregating data masks underlying patterns. When a factor distorts the overall picture, but distortion goes away when underlying data are examined. Continuing with our example, separating earnings data by level of education shows that the relative number of college graduates increased significantly from 2000 to 2013. In 2000, the ratio of college graduates to total workers was 27,564 to 88,730, or 31%. Whereas in 2013, their ratio was about 39%. This shift in the level of educational attainment, plus the fact that better educated workers are paid higher wages, helps to explain the counterintuitive results. Without careful consideration, one can be led to an incorrect conclusion. Another example, the Berkeley gender discrimination case. Data from a 1973 study showed persuasive evidence that University of California at Berkeley was practicing gender discrimination in graduate school admissions. Here we have a table. Out of 8,442 male applicants, 3,714 were accepted, which is 44% acceptance rate. You get this 44% acceptance rate by dividing 3,714 by 8,442 and multiplying it by 100%. For females, there were 4,321 applicants. Accepted were 1,512 applicants with acceptance rate of 35%. Graduate school admissions are based on departmental selections. Let's study how the male and female applicants might have been divided among two departments, math and English. In this table, we broke down the applicants by departments, mathematics and English department. Notice that in the mathematics department, the acceptance rate for male applicants was 25%, and acceptance rate for female applicants was 26%. In the English department, the acceptance rate for males was 49 and 9/10%, and for females, the acceptance rate was 55 and 4/10%. The two departments actually accepted a larger percentage of female applicants than male applicants. Most women apply to the math department, where it is more difficult to be accepted, but most men apply to English, where it is less difficult. Another example. The following table shows the batting record in 2010 of two Major League Baseball teams, the Chicago Cubs and the Oakland Athletics. Which team had the higher indoor batting average? Which team had the higher outdoor batting average? Which team had the higher overall batting average? Solution. We calculate the average for the Chicago Cubs playing indoors as follows. The average indoors is equal to hits divided by at-bats. That is the number of times an athlete was able to hit the ball divided by the number of times the athlete was attempting to hit a ball. This ratio is equal to 29 thousandths, or 29%. We calculate averages for Chicago Cubs and the Oakland Athletics both indoors and outdoors in a similar fashion. The results are shown in the following table. Here the average for Chicago Cubs was 29% indoors and 25 and 3/10% outdoors. The average for Oakland Athletics was 29 and 2/10 indoors and 25 and 5/10 outdoors. Oakland Athletics performed better both indoors and outdoors. Now we find the overall averages. Altogether, the Chicago Cubs got a total of 134 plus 1,280, which is equal to 1,414 hits out of 462 plus 5,050, which is 5,512 trips to the plate. Therefore, overall average for Chicago Cubs is hits divided by at-bats, and that's equal to 1,414 divided by 5,512, or about 25 and 7/10%. A quick review, how to calculate percentages. To calculate p% of a quantity, we'll multiply the quantity by p divided by 100. P% of quantity is p divided by 100 times quantity. To find what percentage of a whole part, percentage is equal to part divided by whole times 100%. For example, find 45% of 500. 45% of 500 is 45 divided by 100 times 500, which is equal to 225. Find what percentage of 140 is 35. Percentage is equal to part divided by whole times 100, which is equal to 35 divided by 140 times 100%, and that's 25%.